There is a number hidden in the oldest light in existence, and for more than 20 years it has refused to appear. The most sensitive instruments ever built have searched for it. A faint, swirling pattern pressed into the radiation left over from the birth of everything. If the standard story of how the universe began is correct, that pattern should be there. It is not. The tensor-to-scalar ratio, the quantity that measures it, now sits below 0.02, and still there is nothing. Decades of effort, and the promised signal never arrived. What does it mean when the evidence we expected to find does not come? Some physicists have an answer, and it is not a small one. They call it the Ekpyrotic Universe, and they propose that the Big Bang was not the beginning. Our universe, they argue, was born not from a single point of infinite density, but from a collision. Two vast, higher-dimensional membranes drifting through a hidden fifth dimension, crashing together and igniting everything we call reality. From that idea descended the cyclic models, a cosmos with no first moment, bouncing through what may be an eternity. By the end of this video, you will understand what these membranes are, how a slow contraction can do the work that inflation claims to do, why the missing signal in the microwave background has become a battleground, and what this strange model quietly assumes about whether the universe needs a beginning at all. If you find value in explorations like this, in understanding the deep puzzles that keep physicists awake at night, consider subscribing to the channel, which helps these deep dives reach more curious minds. Now, let us begin. Part 1. Begin with a word. Ekpyrotic. It comes from the Greek ekpyrosis, meaning out of fire or conflagration. It was borrowed from the ancient Stoics, who imagined a cosmos that periodically dissolved into flame and was reborn. The physicists who revived the word in the year 2001 were not Stoics. They were theoretical cosmologists working at the frontier of string theory, and they chose the word deliberately, because the model they were proposing replaced the familiar fireball of the Big Bang with a fire of a different kind, a fire kindled by collision. In 2001, 4 physicists, Justin Khoury, Burt Ovrut, Paul Steinhardt and Neil Turok, published a paper with a title that sounds like science fiction and reads like mathematics. The Ekpyrotic Universe, Colliding Branes and the Origin of the Hot Big Bang. It appeared in Physical Review D, and it is widely cited as the birth of the idea. The proposal was radical, and its authors knew it. Burt Ovrut of Princeton described it plainly. "It's a very radical idea we have," he said, and he added something stranger still. In this picture, he explained, time zero was just a marker, that the universe really existed long before that. Sit with that for a moment. In the standard account, time zero is the beginning. It is the edge of everything, the moment before which there is no before. The Ekpyrotic model takes that edge and erases it. Time zero becomes a mile marker on a road that stretches back behind it. To understand how anyone arrives at such a claim, we have to understand the thing it was built to replace, and the thing it was built from. The thing it was built to replace is inflation. the thing it was built from, is string theory. Let us take them in turn, and let us take them neutrally, not yet asking whether they are true, only asking what they say. First, the problem that both models exist to solve. When we look out at the cosmic microwave background, the faint glow of radiation released about 380,000 years after the Big Bang, we find something that should not be there. The temperature of that radiation is almost exactly the same in every direction. Point your instrument at one edge of the sky and then at the opposite edge, and the two regions agree to within a few parts in 100,000. They are, for all practical purposes, the same temperature. This is strange, and here is why. In the standard hot Big Bang, those two regions have never been in contact. Light, the fastest thing there is, has not had time since the beginning to travel from one to the other. They are causally disconnected. Each lies outside the other's horizon. And yet they share a temperature, as if they had once sat together long enough to settle into agreement. This is the horizon problem. How regions that never touched came to look identical. There is a second puzzle, close beside it. The geometry of the universe, as far as we can measure, is flat. Flat to extraordinary precision. Space is not curved like the surface of a sphere, and not warped like a saddle. On the largest scales, it is Euclidean. But flatness in cosmology is unstable. Any tiny initial curvature should have grown enormously as the universe aged. For the universe to be as flat as we see it now, it had to begin almost perfectly flat, finely balanced on a knife's edge. This is the flatness problem, the puzzle of why the universe is so flat. The mainstream answer, for more than 40 years, has been inflation. In 1981, the physicist Alan Guth proposed that in the first unimaginably small fraction of a second, around 10 to the minus 35 seconds after the beginning, the universe underwent a burst of exponential expansion. A patch smaller than a proton was stretched in an instant to cosmic scale. Inflation solves the horizon problem, because the entire visible universe grew from a single tiny region that had been in contact before the stretching began. It solves the flatness problem because exponential expansion dilutes any initial curvature to nothing, the way the surface of an inflating balloon looks flatter and flatter the larger it grows. Inflation is driven, in the theory, by a scalar field, the inflaton, rolling slowly down a nearly flat potential. And here we meet our first equation, the one that governs all of cosmic expansion. It is the Friedmann equation, derived by Alexander Friedmann in 1922 from Einstein's general relativity. Spoken aloud, it says, the square of the expansion rate equals 8 pi g over 3 times the energy density. H squared equals 8 pi g over 3 times rho. H is the Hubble parameter, the rate at which space expands. Rho is the total energy density, everything the universe contains. The equation is simple and it is merciless. Tell it what fills the universe, and it tells you how the universe moves. Inflation fills the universe with the energy of a slowly rolling field, and the Friedmann equation responds with exponential growth. The theory of inflation has been enormously successful. It predicts a nearly scale-invariant spectrum of density fluctuations, ripples of almost equal strength across all scales, which is precisely what we observe. The number that measures the tilt of that spectrum, the scalar spectral index, n sub s, is measured by the Planck satellite at 0.9649 plus or minus 0.0042. That is close to 1, but not exactly 1. A slight reddening, exactly the kind of small deviation inflation predicts. When the Planck collaboration published its results, it stated that they were fully consistent with the predictions of inflation. So we should be fair and we should be clear. Inflation is the mainstream. It is the consensus. Most working cosmologists regard it as validated by the cosmic microwave background. Any alternative begins its life as an underdog. And yet, inflation has a soft spot, acknowledged even by those who built it. It does not explain its own beginning. Inflation describes what happens once the universe is already there, already expanding, already equipped with an inflaton field poised at the top of its potential. It does not remove the initial singularity, that point of infinite density at the very start. It pushes the singularity backward, behind the curtain of inflation, but it does not erase it. Alan Guth himself acknowledged that the theory has not been tested observationally in any detail. And the astronomer Mario Livio, writing in 2001, put it bluntly. Inflation theory has not been tested observationally in any detail. Keep that admission in mind. We will return to it. This is the gap into which the Ekpyrotic model stepped. Now the second ingredient, the strange architecture the model is built from. String theory and its larger cousin M theory propose that the fundamental constituents of reality are not point particles, but tiny vibrating strings, and that they live not in 4 dimensions, but in 11. The extra dimensions are normally imagined as curled up, too small to see. But in one particular version of M theory, worked out by Peter Horrover and Edward Witten in the mid-1990s, one of those extra dimensions is special. It is an interval, bounded at each end by a wall. And these walls are not metaphors, they are branes, short for membranes, vast sheets that stretch across all of space, the boundaries of a higher dimensional volume the theorists call the bulk. Picture it as far as a 3-dimensional mind can. 2 enormous parallel sheets separated by a gap along a 5th dimension. Our entire universe, every galaxy, every star, every atom of your body is painted onto one of those sheets. We cannot see the gap because we cannot leave the sheet. Light and matter are confined to the brain. Only gravity, in this picture, reaches across the bulk between them. The separation between the 2 branes is itself a physical quantity, and it has a name, the radion. The radion is a scalar field, a number defined at every point that measures the distance across the 5th dimension. When the radion is large, the branes are far apart. When the radion shrinks to zero, the branes touch. And in the ekpyrotic model, that touch is everything. The two branes, drifting slowly together across the bulk, collide. The kinetic energy of their approach is converted in the instant of collision into a flood of hot, dense radiation and matter, a quark-gluon plasma spread across the entire brane at once. That flood is what we have always called the Big Bang. What does it mean that the Big Bang in this picture is not an explosion in space, but a collision of spaces? This is the central image, and it is worth holding still to look at. There is no single point. There is no center from which everything flies outward. The hot beginning happens everywhere on the brane simultaneously, because the entire brane strikes the other one all at once, like two flat panes of glass meeting face to face rather than corner to corner. The uniformity of the early universe, the very thing the horizon problem struggles to explain, is built into the geometry of the collision. The branes were flat and parallel, so the fire they kindled was even. The science writer Paul Sutter, summarizing the model for a general audience, described the approach of the branes this way. The branes take a long, leisurely time drifting toward each other, he wrote. More than enough for everything to settle into quiet agreement before the bounce. That is the ekpyrotic answer to the horizon problem. The regions of the sky that appear never to have been in contact were in contact, not after the bounce, but before it, during the long, slow drift of the branes through the bulk. The agreement was reached in the contraction, not in the expansion. And this is the deep structural difference between the two models, the one that everything else hangs from. Inflation solves the horizon problem by violent expansion after the beginning. Ekpyrosis solves it by slow contraction before the beginning. Inflation says the universe was tiny and connected, then stretched apart faster than light could keep up. Ekpyrosis says the universe was already vast, and a long contraction brought distant regions into causal contact, while the cosmos was still in its previous phase. To make this work, the contraction cannot be ordinary. It must be a particular kind of slow squeeze, and the requirement is captured by a single quantity, the equation of state, written W. The equation of state relates the pressure of whatever fills the universe to its energy density. W equals pressure divided by density. For ordinary matter, W is small. For the ekpyrotic phase, W must be enormous, much greater than 1. This ultra-stiff condition is what physicists mean when they call the contraction ekpyrotic. It is a contraction so dominated by the energy of a single steep scalar field that the energy density rises far faster than anything else as the universe shrinks. There is a way to arrange for W to be so large. You give the scalar field a particular potential, a particular shape to the landscape it rolls across. In the ekpyrotic models, that shape is a steep negative exponential. Written as an equation, v of phi equals minus v naught times e to the minus c phi. V is the potential energy of the field. V0 is a positive constant. The letter C is a number, and it must be large. The minus sign matters. The potential is negative, a deep descending valley rather than a gentle hill. As the field rolls down this steep negative slope, the equation of state climbs to the towering values the model requires. Motion of that field obeys a second equation, the one every scalar field in an expanding or contracting universe must satisfy. Phi double dot plus 3h phi dot plus the derivative of v with respect to phi equals 0. Spoken plainly, the field accelerates according to the slope of its potential, slowed or driven by the friction of cosmic expansion. It is the cosmic equivalent of a ball rolling in a bowl, with the expansion of the universe acting as a kind of drag. Notice what the steepness of that potential is doing, and remember it. The parameter c, the number that sets how steep the slope is, has to be large for the model to work. Not approximately. The whole mechanism depends on it. We are told the universe is flattened and smoothed because this one number in this one potential takes a large value. We will come back to that number. For now, notice that it is there. There was an idea before the ekpyrotic idea, and honesty requires that we name it, because the ekpyrotic authors themselves did. In the early 1990s, two Italian physicists, Gabriele Veneziano and Maurizio Gasparini, proposed what they called the pre-Big Bang scenario. It was also rooted in string theory. It also imagined that the universe had a history before the Big Bang. It began, in their picture, in an empty, cold, nearly featureless string vacuum, and underwent a phase of accelerating growth, a kind of superinflation, before reaching the hot, dense state we observe. The pre-Big Bang model and the ekpyrotic model are cousins. They share the instinct that the singularity is not the beginning, but a transition. The ekpyrotic authors noted that their model bears some relation to the pre-Big Bang scenario, while differing in one important way. Ekpyrosis, they wrote, avoids inflation or deflation altogether. The pre-Big Bang model struggled with technical problems, an unstable runaway field called the dilaton, and difficulty producing the right spectrum of fluctuations, and it was largely set aside after 2000. But it established the template. The idea that time runs backward through the Big Bang did not begin with the ekpyrotic paper. It was in the air. Let us also be precise about what kind of beginning the ekpyrotic model offers, because the language matters. In its earliest form, the model still had a kind of singularity at the moment of collision. The instant when the radion reaches zero and the branes touch is a moment of extreme conditions that the simple theory could not fully describe. The ambition, stated from the start, was a non-singular bounce, a smooth transition from contraction to expansion, with no infinite density anywhere, no point where the equations break down and surrender. As Steinhardt and his colleagues put it, the universe existed long before time zero, and time zero was just a marker. The collision is dramatic, but in the mature versions of the theory, it is meant to be finite, physical, and describable. A bounce, not a wall. This was the proposal in its first form. A pair of branes in a 5-dimensional bulk. A radion measuring the gap between them. A steep negative potential driving a slow, stiff contraction that smooths and flattens the cosmos. A collision that converts motion into fire. And a claim, quiet but enormous, that the fire we call the beginning was nothing of the kind. In 1998, 3 years before the Ekpyrotic paper, astronomers studying distant exploding stars, the Type 1a supernovae, made a discovery that would later become essential to this entire story, though no one knew it at the time. The teams, led by Saul Perlmutter, Brian Schmidt, and Adam Rees, found that the expansion of the universe is not slowing down, as everyone expected, but speeding up. Something is pushing the cosmos apart. We call it dark energy, and its discovery earned the Nobel Prize in 2011. For the Standard Model, dark energy was a surprise and an embarrassment, a number no one could explain. For the descendants of the Ekpyrotic model, as we will see in Part 2, dark energy would turn out to be not an embarrassment, but a necessity. Keep it in view. We are building towards something. For now, we have the original Ekpyrotic picture in place. A single collision, a single bounce, a universe lit from the crash of 2 membranes. But a single bounce raises an obvious question. If the universe existed before the collision, it was doing something. And if it can bounce once, there is no clear reason it cannot bounce again. That thought turns a single event into a cycle, and the cycle is where the model becomes something far stranger and far more ambitious. That is where we turn next. In 2002, 1 year after the original Ekpyrotic paper, Paul Steinhardt and Neil Turok published a follow-up in the journal Science. Its title named the new ambition directly: a cyclic model of the universe. The idea was to take the single collision and make it eternal, to embed the brane collision into an endless sequence of cycles, each one a contraction, a bounce, an expansion, and a slow return to contraction, repeating without end. In this picture, the universe does not begin and it does not end. It cycles. Every Big Bang is preceded by a big crunch that is not quite a crunch, a bounce, and followed by another trillions of years later. We are not living in the aftermath of the beginning. We are living in one cycle of an unbounded series, near the bounce, far from any first cause, and far from any last. The proponents of this view do not hide what it implies. Steinhardt has said, simply, that time zero was just a marker, that the universe really existed long before the moment we have always called the start. The cyclic model takes the boldest reading of that sentence and runs it to infinity. There is no first cycle that needs explaining, the model proposes, only cycle after cycle, backward without limit. What does it mean to live in a universe with no first moment? Hold the question. We are presenting, not yet examining. The early cyclic model of 2002 was elegant, but it had 3 serious problems, and the people who built it have been candid about all 3. We name them now, neutrally, because they organize the deeper exploration to come. The first problem is the bounce itself. In the original cyclic model, the transition from contraction to expansion still passed through a singular state, a moment of crushing density where general relativity, the theory we use to describe gravity, stops giving answers. A model that promises to abolish the singularity cannot have a singularity hiding at the heart of every cycle. The bounce had to be made smooth, non-singular, fully describable. That is a tall order, because standard general relativity, left to itself, forbids a smooth bounce. We will see in Part 2 the exotic ingredient the theorists reached for to get around that prohibition, and what it costs them. The second problem is anisotropy, the problem of lumpiness and direction. A contracting universe is a dangerous place. Tiny irregularities, tiny differences in how fast it shrinks along different directions, tend to grow as the contraction proceeds. Grow them enough, and the smooth, orderly bounce dissolves into chaos, a violent, churning, direction-dependent collapse that physicists call, after the 3 scientists who studied it, the BKL instability. A naive bouncing universe does not bounce cleanly. It shatters. The ekpyrotic phase, with its ultra-stiff equation of state, is meant to be the cure. Whether the cure truly works has been one of the longest arguments in the field. We will examine it closely. The third problem is entropy. The second law of thermodynamics says that disorder, entropy, always increases. In a cyclic universe, that creates a trap. If every cycle adds to the total disorder, then the cycles cannot have been running forever because the disorder would already be infinite. Run the cycles backward and they should grow smaller, hotter, more disordered, until the whole scheme collapses. This is an old objection, raised against cyclic cosmologies as far back as the 1930s by the physicist Richard Tolman. Any modern cyclic model has to answer Tolman, and the answer the ekpyrotic theorists give is one of the most counterintuitive moves in the entire theory. For nearly 2 decades, these 3 problems, the singular bounce, the anisotropy, the entropy, sat on the model like weights. And then, in 2019, came a serious attempt to lift all 3 at once. That year, Anna Ijjas and Paul Steinhardt published a paper in Physics Letters B with a title as bold as the original: A New Kind of Cyclic Universe. Anna Ijjas, a cosmologist who has worked at the Max Planck Institute in Germany and at Princeton, became one of the central architects of the modern theory. The new cyclic model made several striking moves. It dispensed with the extra dimensions and the literal branes. working instead in our ordinary 3 dimensions of space and 1 of time, and replaced the brane collision with the dynamics of 2 scalar fields. One field drives the ekpyrotic contraction with that enormous equation of state. The other behaves like dark energy, the very acceleration discovered in 1998, and it governs the long, slow expansion that precedes each contraction. Here, the discovery of dark energy stops being an embarrassment and becomes the engine of the cycle. In the new cyclic model, the accelerating expansion we observe today is not a puzzle to be explained away. It is the mechanism that keeps the cosmos smooth and drives it toward the next phase. The dark energy field accelerates the universe for an immense span of time, somewhere between 10 to the 14th and 10 to the 17th years, vastly longer than the present age of the universe, diluting the debris of the previous cycle across an enormous volume. Then, that field's influence winds down. The ekpyrotic field takes over, and a new contraction begins. The acceleration we see is, in this view, a cosmic clock. It is counting down to the next bounce. And notice what this does to the entropy problem. Because each cycle includes a long phase of net expansion, the entropy of the previous cycle is spread out, diluted, across a far larger volume before the next contraction begins. The disorder is not destroyed. It is scattered so thinly that each new cycle begins, in its own local patch, effectively fresh. We can write the logic as an equation. The entropy after a cycle equals e to the 3n times the entropy before, where n is the number of e-folds of net expansion during the dark energy phase. With n as large as 60, that factor is a number like 10 to the 78. The accumulated disorder of an entire cosmos is divided across a volume so vast that, per region, it rounds to nothing. The science writer Paul Sutter described the trick as a way to dilute all that accumulated entropy across an enormous volume. We will ask in Part 3 whether dilution is truly an answer to Tolman, or only a relocation of the question. For now, note the elegance, and note the move. What does it mean that the second law of thermodynamics, which everywhere else only drives disorder upward, can be made to begin each cycle clean, not by being defied, but by being outrun? The new model also claims something its proponents prize above almost everything: predictability. Anna Ijjas and Paul Steinhardt have written that, in their model, all coarse-grained properties of the universe are deterministically set by the governing classical equations. There is, they say, no quantum runaway that leads to the multiverse effect. This is a pointed claim, and it is aimed squarely at inflation. We will unpack the quarrel in Part 2, but hold the phrase, deterministically set by the governing classical equations. It is a confident sentence. We will test the confidence later. It would be wrong to present the ekpyrotic and cyclic models as the only alternatives to inflation, or to suggest that all cyclic thinkers agree. They do not. The most famous rival cyclic picture comes from Roger Penrose, the British mathematician and Nobel laureate, who proposed around 2007 a scheme he calls conformal cyclic cosmology. Penrose's universe also repeats, but the physics could hardly be more different. There are no branes and no bounce. Instead, Penrose imagines that the infinitely distant future of one universe, what he calls an eon, becomes, through a geometric transformation, the Big Bang of the next. For this to work, every massive particle must eventually decay away, until only massless radiation remains, and the universe forgets its own scale. Penrose deals with the entropy problem in his own way. He argues that as black holes evaporate over unimaginable spans of time, the universe's gravitational disorder is effectively reset. Both the Ekpyrotic model and Penrose's model and cyclic alternatives to the standard beginning. Both refuse the single creation event. But ekpyrosis resets entropy by dilution through expansion, while Penrose resets it by stripping the universe of mass. They are two different bets on the same instinct. And there are others. Loop quantum cosmology, with its quantum gravity bounce. String gas cosmology. A whole family of what are called bounce cosmologies, all sharing the idea that a contraction preceded our expansion. The ekpyrotic and cyclic models are the most developed members of this family, the ones with the most worked-out machinery and the most specific predictions. But they belong to a broader rebellion against the idea that the Big Bang was the first event. So let us assemble the cast and the claims as Part 1 closes, before we descend into the technical battlegrounds. The mainstream is inflation, Guth's exponential expansion, tested against the cosmic microwave background, regarded by most cosmologists as validated, but admittedly untested in its deepest details, and admittedly silent about its own origin. Against it stand the ekpyrotic and cyclic models, the work of Khoury, Ovrut, Steinhardt, Turok, and later Ijjas, proposing that the universe is smoothed not by stretching, but by squeezing, that the Big Bang was a bounce, and that the cosmos may have no beginning at all. Even those sympathetic to the new model speak carefully. Alan Guth, the father of inflation, said of the ekpyrotic idea, "I don't think it's by any means yet a real rival to inflation, but it is a model well worth pursuing." Mario Livio, the astronomer, saw in it a virtue inflation lacked, a chance to be tested and possibly proven wrong. The ekpyrotic model, he said, provides us with a potential true test that can distinguish between it and inflation. And Paul Sutter, surveying the whole construction with evident affection, called the picture beautiful, and then said the thing that haunts the field. "It is good," he allowed. "It is just a shame," he said, "that it doesn't work." Whether it works is the question of Part 2 and Part 3. In Part 2, we go where the argument is decided, into the fluctuations of the cosmic microwave background, the missing gravitational waves, the chaos of the contracting universe, and the exotic physics required to make a universe bounce. The mathematics is real, the instruments are real, and the stakes, as we will see, run deeper than cosmology. Part 2. A cosmological model is not judged by how beautiful its story is. It is judged by whether it can reproduce the universe we see. And the universe we see is written with astonishing precision into the cosmic microwave background. So let us go there, into the patterns of the oldest light, and ask what the ekpyrotic model must do to survive contact with the data. The first test is the spectrum of density fluctuations. The early universe was not perfectly smooth. It carried faint ripples, regions slightly denser than average, which would later grow, under gravity, into galaxies and clusters and the great cosmic web. The strength of those ripples across different scales is described by a power spectrum, and the power spectrum has a tilt. We can write it as an equation. The power, P sub zeta, is proportional to the wave number k raised to the quantity n sub s minus 1. The wave number k is a measure of scale, large K for small patches, small k for vast ones. And n sub s, the scalar spectral index, is the tilt. If n sub s were exactly 1, the ripples would have equal strength on every scale. Perfect scale invariance. The measured value is 0.9649 plus or minus 0.0042, close to 1, slightly less than 1, slightly red. Inflation produces this spectrum naturally, from the quantum jitter of the inflaton field as space expands. The ekpyrotic model has a harder road, and the road it takes is one of the most distinctive features of the theory. A single field, contracting on its own, does not produce the right ripples. So the model uses two fields, and a mechanism with a name worth knowing: the conversion of entropy perturbations into curvature perturbations. During the ekpyrotic phase, fluctuations build up not in the overall density, but in the relative balance of the two fields, what physicists call entropy or isocurvature modes. These have nearly the right shape. Then, around the time of the bounce, those entropy modes are converted into the curvature modes, the actual density ripples that we observe. Through this two-step dance, the ekpyrotic model can produce a nearly scale-invariant spectrum, with n sub s in the range of about 0.95 to 0.97. It can, in other words, match the observed tilt. But notice what matching required. It required two fields rather than one. It required a conversion mechanism timed to the bounce. It required, as we will see, specific choices about the shape of the potential. Inflation gets its spectrum from one field and a quantum effect. Ekpyrosis gets its spectrum from two fields and a carefully arranged conversion. Both reach the same destination. Keep in mind how differently they travel. Now the second test, and this is the one that has become a battleground, the test of the missing gravitational waves. When the early universe ripples, it ripples in two ways. There are the density ripples, the scalar perturbations, which we have just discussed, and there are gravitational waves, ripples in the fabric of space-time itself, the tensor perturbations. Inflation, because it stretches space so violently, generically produces a sea of primordial gravitational waves. Those waves leave a faint, swirling fingerprint in the polarization of the cosmic microwave background, a pattern physicists call B-mode polarization, a curl in the orientation of the ancient light that only gravitational waves can produce. The strength of that signal is measured by the tensor-to-scalar ratio, written R, the ratio of the tensor spectrum to the scalar spectrum. As an equation, it is simply R equals P sub t over P sub zeta, the power in gravitational waves divided by the power in density ripples. For standard inflation, theory gives a clean relation. R equals 16 times epsilon, where epsilon measures how quickly the inflaton rolls. Many inflationary models predicted R around 1/10. The Ekpyrotic model predicts something radically different. Because the universe is contracting rather than expanding violently, it does not pump energy into long wavelength gravitational waves. The tensor spectrum is what physicists call blue, its power concentrated at tiny scales, vanishing at the large scales the cosmic microwave background probes. The Ekpyrotic prediction for R at observable scales is effectively zero. Not small, almost nothing. R below 10 to the minus 5, far beyond any foreseeable detection. This is the cleanest difference between the two models. Inflation, in many forms, says there should be primordial gravitational waves, and we should be able to find their imprint. Ekpyrosis says there are no observable primordial gravitational waves at all. One predicts a signal, the other predicts silence. And so the search for B modes became a direct contest between two pictures of the beginning. The story of that search includes one of the most dramatic episodes in recent cosmology. In March of 2014, a collaboration running an instrument at the South Pole called BICEP2 announced that it had found the signal, primordial B modes with R around 0.2. For a few weeks, it was hailed as a discovery of historic proportions, a direct glimpse of inflation in action. And then it unraveled. A more careful analysis, combining BICEP2 with data from the Planck satellite, showed that the swirling pattern was not primordial at all. It was dust, polarized emission from grains of dust in our own galaxy, masquerading as a signal from the beginning. The claim was withdrawn. What does it mean that the most celebrated detection of the echo of creation turned out to be foreground contamination in our own backyard? It means the search is brutally hard. And it means the universe does not hand over its origins easily. After the dust, the limits only tightened. The combined data from the BICEP and Keck arrays, together with Planck, pushed the bound on R down and down to less than 0.056, and then by 2022 to less than 0.032 at 95% confidence. No primordial gravitational waves have been found. Every year the silence deepens, and every year the upper limit falls closer to zero. Closer, that is, to the Ekpyrotic prediction. We must be scrupulously fair here, because this is the kind of place where enthusiasm outruns evidence. A non-detection is not a confirmation. Inflation is a broad family of models, and many of its members, the so-called small field models, predict an R so low that current instruments could never have seen it. A bound of R below 0.032 rules out some inflationary models. It does not rule out inflation. The honest statement is the one the field makes. The the data are, so far, consistent with ekpyrosis and consistent with low-energy inflation, and we cannot yet tell them apart. This is why the next generation of instruments matters so much. Consider what is coming. The Simons Observatory in the Atacama Desert of Chile is designed to measure R to a precision of around 0.0012. CMBS-4, a proposed ground-based array for around the 2030s, aims to reach R below 0.001. Lightbird, a planned Japanese satellite, targets a similar sensitivity from space. These instruments will either find the gravitational wave signal that large field inflation predicts, or they will push the limit so low that the ekpyrotic prediction of near zero R becomes the more natural reading of the data. A forecast for CMBS-4 states the stakes precisely. It will either detect inflationary gravitational waves above R of 0.003 at high significance, or limit R below 0.001. One of those two outcomes is coming. The battleground is being prepared even now. It is worth pausing to remember how this whole field of precision was built, because the instruments did not appear all at once. The lineage is a story of escalating clarity. In 1964, Arno Penzias and Robert Wilson, working with a radio antenna in New Jersey, stumbled upon the cosmic microwave background itself. The faint hiss they could not eliminate turned out to be the afterglow of the early universe. In 1989, the COBE satellite measured that glow with new precision, and, in the early 1990s, mapped its first faint temperature ripples. At the turn of the millennium, balloon-borne experiments named Boomerang and Dazzy measured the characteristic scale of those ripples and confirmed that space is flat. Then came WMAP, mapping the sky from 2001 through 2010, pinning the spectral index near 0.96. And then Planck, launched by the European Space Agency in May of 2009, refining the map to a resolution of a few arc minutes and delivering the precise numbers we have been quoting: the spectral index, the bounds on gravitational waves, the limits on non-Gaussianity. Each instrument sharpened the picture. Each one narrowed the room in which any theory of the beginning could hide. And there is one feature of that map that the ekpyrotic proponents point to with particular interest: a small anomaly at the largest scales of all. When we look at the cosmic microwave background at its lowest multipole, the quadrupole, the pattern that varies across the whole sky, the power is anomalously low. It sits at roughly 6% of what the standard model predicts, a suppression of large-scale correlations significant at something like the 2 to 3 sigma level. It is not a decisive anomaly. It may be a statistical fluke, because at these vast scales we have only one sky to measure and a handful of independent patches to measure it with, an irreducible uncertainty cosmologists call cosmic variance. But ekpyrotic proponents argue that their contracting phase could suppress that large-scale power naturally, through a feature in the dynamics of the bounce, where standard inflation would need an ad hoc step inserted by hand into the inflaton's potential. We can capture the idea in a toy equation. The power spectrum is approximately P0 times the quantity 1 minus alpha times e to the minus k over k star, a smooth form in which the power drops away at the largest scales, small k. Whether that dip is a genuine signature of a bounce or merely noise in a single sky, no one can yet say. But it is the kind of subtle clue the model hopes will one day tip the balance. To feel the weight of what these instruments are measuring, hold the scale in your mind for a moment. The observable universe stretches to a radius of about 46 billion light-years. In metric terms, that is roughly 4.35 times 10 to the 26th meters. In imperial terms, around 2.7 times 10 to the 13th miles. A distance so far beyond human experience that the number is a symbol, not a quantity we can feel. Light itself, the fastest thing there is, crosses only about 9.5 trillion kilometers, about 5.9 trillion miles, in a single year. The cosmos has been expanding for some 13.8 billion years, at a present rate, the Hubble constant, of about 67 kilometers per second for every megaparsec of distance. And the cyclic model asks us to set even that staggering age beside the length of a single cycle, which by some estimates runs to 10 to the 26th years, with the dark energy phase alone lasting longer than the present universe has yet existed. Our entire recorded history, every civilization, every life, is a vanishing sliver near one bounce in a sequence the model says has no first term. This is the part that stays with me, not the scale. The scale only numbs. It is the placement. If the cyclic picture were true, we would not be living near the dawn of things, as the standard story lets us imagine. We would be adrift somewhere in the middle of an endless repetition, with an eternity of cycles behind us and an eternity ahead. Our Big Bang merely the latest in a series without beginning. Take a moment before we go on and ask yourself honestly, which is harder to accept? A universe that began, and therefore points beyond itself for a cause, or a universe that never began at all, stretching backward forever with no first cause and no first light? Hold that question, we will need it before the end. There is a third test, and here the Ekpyrotic model has already taken damage. It is the test of non-Gaussianity. If the primordial ripples were generated by simple quantum fluctuations, they should follow a Gaussian distribution, the familiar bell curve, almost perfectly. Deviations from that bell curve are measured by a parameter called FNL. Simple single-field inflation predicts FNL very close to zero. Many ekpyrotic models, because of that two-field conversion mechanism, naturally predict a large FNL. And here is the problem. The Planck satellite measured the local FNL at 2.7 plus or minus 5.8, entirely consistent with zero. The large non-Gaussianity that the simplest ekpyrotic models predicted is not there. This matters and the model's proponents know it matters. The original ekpyrotic predictions of large non-Gaussianity were, in effect, falsified. The theory had to be adjusted, its conversion mechanism refined, its parameters tuned, to bring the predicted FNL down into agreement with the data. When the Planck collaboration analyzed non-Gaussianity, it stated that the data significantly limit the viable parameter space of ekpyrotic scenarios. That is, the model's own house being constrained by observation. Inflation, in its simplest form, predicted near-zero non-Gaussianity, and the data agreed. Ekpyrosis predicted large non-Gaussianity. The data disagreed, and the theory was modified to fit. Both stories are now consistent with the measurement, but they arrived at consistency by different paths, one by prediction, one by correction. Remember that asymmetry. We will return to what it means when a theory must be repaired to match what it claimed to predict. Now we descend into the deepest technical problem of all, the one that nearly killed bouncing cosmology decades before the ekpyrotic model was born. The problem of the contracting universe tearing itself apart. When a universe contracts, anisotropy is the enemy. Imagine the cosmos shrinking, but shrinking slightly faster in one direction than another. The difference does not stay small. The energy stored in that anisotropy, which physicists call shear, grows as the universe contracts, and it grows fast. As an equation, the shear energy density, rho sub sigma, is proportional to A to the -6, where A is the scale factor, the size of the universe. As A shrinks, A to the -6 explodes. Left unchecked, the shear comes to dominate everything, and the smooth contraction degenerates into the violent, chaotic, direction-flipping collapse known as the BKL instability, named for Belinsky, Kalatnikov, and Lifshitz, who mapped this chaos near a singularity. A universe in BKL chaos does not bounce. It is ground into a mixmaster of competing distortions, and any hope of a clean, orderly new beginning is lost. This was long considered a fatal flaw for any bouncing model, and the ekpyrotic phase is the proposed cure. Here is the logic, and it is genuinely elegant. The shear grows as A to the -6. But the ekpyrotic field, with its enormous equation of state, W far greater than 1, has an energy density that grows as A to the -n, where n is much greater than 6. The steep potential makes the field's energy rise faster as the universe shrinks than the shear does. So, even though the shear is growing, the ekpyrotic energy outpaces it, and the ratio of shear to ekpyrotic energy drops towards zero. Contraction becomes, in the technical phrase, a strong, homogeneous attractor toward isotropy. The universe is smoothed precisely because the steep field's energy overwhelms the anisotropy that would otherwise destroy it. We can be quantitative. The scaling of the ekpyrotic phase follows a power law. The scale factor A is proportional to -t raised to a power p, where p equals 2 over c squared, and c, you will recall, is the steepness of that exponential potential. For large c, p P is tiny, the contraction is ultra-slow, and the equation of state W is enormous. The anisotropy decays relative to the ekpyrotic energy by a factor of e to the minus 2n per e-fold of contraction. And here is the striking number. The model needs only about 10 to 12 e-folds of ekpyrotic contraction to suppress the anisotropy by a factor of around e to the minus 20, roughly a billion-fold. Compare that to inflation, which typically requires more than 60 e-folds of expansion to do its work. The ekpyrotic contraction is, in this sense, remarkably efficient. A short, steep squeeze does what a long, vast stretch must do for inflation. What does it mean that the cure for cosmic chaos is to make one field's energy climb faster than disorder can grow? It means the entire smoothness of the Ekpyrotic universe rests on the steepness of that potential, on C being large, on W being far greater than 1. Make the slope gentler and the anisotropy wins. The model lives or dies by the steepness of a single curve. We have now seen that requirement appear 3 times, in the equation of state, in the perturbation spectrum, and now in the taming of chaos. 3 times the steep potential. Hold that. Then there is the bounce itself, the moment of transition from contraction to expansion, the heart of the whole enterprise. And here, the ekpyrotic model must do something that ordinary physics forbids. In general relativity, a smooth, non-singular bounce requires violating what is called the null energy condition. The requirement, written ρ plus p greater than or equal to 0, that energy density plus pressure stays non-negative. Ordinary matter and ordinary fields obey it. But to turn a contraction into an expansion without passing through a singularity, you need, for a brief moment, energy density plus pressure to go negative. You need to violate the null energy condition. Standard physics regards such violation with deep suspicion, because the fields that usually accomplish it are pathological. They carry instabilities called ghosts, runaway modes that would tear the theory apart. The achievement that revived the cyclic model was finding a way to violate the null energy condition without summoning a ghost. In 2016, Anna Ijjas, Paul Steinhardt, and Abraham Loeb demonstrated a stable, non-singular bounce using a special class of scalar fields, the Galilean fields, part of a broader family known as Horndeski theories. These fields have carefully constructed interactions that allow the brief, controlled violation of the energy condition needed for the bounce, while remaining free of ghosts and instabilities. It was a genuine technical breakthrough. It is also, let us be honest about it, exotic. The bounce requires a kind of matter we have never observed, behaving in a way ordinary matter cannot, doing the one thing the standard energy conditions forbid, and doing it, the theorists must show, without the whole structure collapsing. As an entry in the model's own ledger, the null energy condition violation is a profound assumption. We name it now neutrally. We will weigh it later. Let us pause and gather the strangeness, because Part 2 has accumulated a great deal of it. And the strangeness is not decoration. It is the texture of the theory. It is strange that the Big Bang, in this picture, is not the beginning of time, but a transitional moment, with an entire history stretching behind it. The usual statement, "the universe had a first moment," is replaced by "time extends before time zero." It is strange that our hot beginning was produced, on this account, by a collision with a parallel universe along a hidden dimension, a literal crash of cosmic sheets, converting the energy of approach into all the matter and radiation there is. It is strange that entropy, which always increases, can be made to effectively reset, not by being destroyed, but by being scattered across a volume so vast by the long, dark energy expansion, that each new cycle begins locally fresh. It is strange that the Ekpyrotic universe needs no quantum uncertainty to seed its structure. Where inflation leans on quantum fluctuations, the Ekpyrotic model is far more classical, its ripples set in large part by deterministic dynamics. Anna Ijjas and Paul Steinhardt stake the theory's predictability on exactly this: properties deterministically set by the governing classical equations. It is strange that gravity's role is inverted. In inflation, gravity is gentle and expansion is everything. In ekpyrosis, gravity grows ferociously strong during the contraction, and, counterintuitively, that strengthening is what makes the universe smooth. And it is strange, perhaps strangest of all, that our late-time cosmic acceleration, the dark energy discovered by accident in 1998, is here recast as a built-in cosmic clock, the slow timer that keeps the branes apart and then, when it winds down, triggers the next contraction. A discovery that embarrassed the standard model is, in the cyclic model, the keystone. We should be clear, finally, about where this all stands as honest science. The ekpyrotic and cyclic models reproduce the known successes: flatness, homogeneity, the near-scale invariance of the density ripples. They predict negligible primordial gravitational waves, which is, so far, consistent with the data. Their modern versions have answered, at least on paper, the three classic objections: the singular bounce, the anisotropy, the entropy. Their proponents argue with real force that the model is now robust and testable. But the case against is equally real, and we present it without flinching, because Part 3 will need it. There is no direct evidence for any of this. No one has observed an extra dimension. No one has observed a brane. The Galilean fields that power the bounce have never been detected in any laboratory. The specific shape of the potential, that steep exponential with its large value of c, is not derived from any deeper theory. It is assumed because the model needs it. The Planck data have tightened the noose on the model's parameter space. And the mainstream of cosmology still regards inflation as simpler: one field, fewer exotic assumptions, and still regards ekpyrosis as a fascinating, unproven alternative. The honest verdict of the field is that the question is open, and that some of the most important pieces of the ekpyrotic story lie, by their very nature, beyond our reach. That phrase, beyond our reach, is where part 3 begins. Because once we ask what we can never test, and why a model needs the precise ingredients it needs, and what it would mean for the universe to have no beginning at all, we have left the territory of measurement and entered a different kind of examination. We have presented the model fairly, as it asks to be presented. Now we test whether its largest claims survive scrutiny. Part 3. For the past hour, I have presented what physicists propose. I have tried to give the ekpyrotic and cyclic models their strongest formulation, their elegance, their answers, their genuine achievements. Many intelligent and sincere people have devoted their careers to this work, and they deserve a fair hearing. They have had one. Now we examine the claims that reach beyond the physics. The claims about beginnings, about causes, about whether the universe explains itself. 3 of them were planted like seeds in everything that came before. We return to them now, one at a time, and we test whether they hold. The first claim is the largest. It is the claim that the cosmos has no beginning and no end, that it has always existed, cycling without limit, and therefore needs no creation and no creator. This is the deepest attraction of the cyclic model, stated plainly by its own architects. Time zero, Burt Ovrut said, was just a marker. The universe really existed long before that. Paul Steinhardt has built an entire cosmology on that sentence. There is no first moment to explain, the claim proposes, because there is no first moment at all. Let us examine it. The appeal is obvious. A universe with a beginning seems to demand a cause for that beginning, something to light the fuse. Remove the beginning, and you seem to remove the demand. An eternal cycle appears to answer the oldest question by refusing to let it be asked. If there was never a first moment, then no one needs to ask what came before it. But look closer at what the model has actually done, because this is where the argument fails. The Ekpyrotic universe is not nothing arranging itself into something. It is a vast, intricate physical system. 2 scalar fields, a steep and precisely shaped potential, a Galilean bounce that violates the energy conditions in exactly the controlled way required, a dark energy epoch tuned to last 10 to the 14th years, and then conveniently switch off. The model does not derive these things, it assumes them. It begins at every cycle and at every moment of its eternal past with the laws of physics already in force, the fields already present, the potential already shaped, the equations already governing. The cyclic universe does not explain why anything exists, it explains how an already existing, already structured, already lawful cosmos moves. And so, the question the model claimed to abolish returns, untouched. Why is there something rather than nothing? Why do these particular fields exist? Why does the radion's potential have the precise steep form the model requires, and not some other form? Why are there laws at all? And why these laws? Making time infinite does not answer a single one of these questions. It merely spreads them across an infinite past. An eternal cosmos is not a self-explaining cosmos. It is the same unexplained cosmos repeated forever. Consider the logic directly. Suppose every cause requires a prior cause, stretching back through an infinite chain of cycles with no first link. Here is the difficulty that the medieval philosophers saw clearly, and that no amount of modern machinery removes. An infinite chain of dependent causes never grounds anything. If link 1 depends on link 2, and link 2 on link 3, and so on, without end, then there is nothing the whole chain hangs from. And a chain of dependencies that hangs from nothing supports no weight at all. The fact that we exist, that this cycle is real, proves that the chain terminates somewhere. It proves that something exists which does not depend on a prior cause, which is itself uncaused, self-sufficient, and not merely one more link. The cyclic model, by pushing the chain to infinity, does not escape this. It hides the terminus and hopes we will not notice that the chain still needs one. And here is the inversion that exposes the move. The proponent of the eternal cycle says, I do not need a first cause, because something has always existed, the cosmos itself, cycling forever. But notice what has just been conceded. They have accepted that something must be eternal, uncaused, and self-existent. That is not a small concession. That is the entire structure of the very conclusion they are trying to avoid. The only question that remains is the nature of that eternal, uncaused, self-existent thing. Is it unconscious matter, fields and branes and potentials that happen for no reason to exist and to be exquisitely arranged? Or is it an intelligent cause with the power to bring a universe into being and the will to shape it? The cyclic model has not removed the eternal reality behind the universe. It has only insisted, without argument, that the eternal reality is mindless. What does it mean that a model built to eliminate the beginning still requires an eternal something to do the work? It means the choice was never between a caused universe and an uncaused one. The choice is, and always was, between an uncaused matter and an uncaused mind. And mindless matter, as we are about to see, cannot account for what this universe contains. That brings us to the second claim, that physical laws and chance fully explain the cosmos, that brane collisions and scalar fields are, in the words of the model, all it takes, and that purpose and design are therefore unnecessary. The proponents stress determinism. All coarse-grained properties of the universe, Ijjas and Steinhardt write, are deterministically set by the governing classical equations. The implication is that once you have the equations, you have everything. No designer required. Let us give this its due, and then let us test it against the model's own machinery. The claim assumes that the laws of physics are brute facts, that they exist, that they take the form they take, and that no further explanation is needed or possible. And it assumes that those laws, running their course, produce a habitable, ordered universe as a matter of routine. But the ekpyrotic model itself refutes that second assumption in its own equations, with its own hands. Remember the steep potential, the number c, which we met 3 separate times. The smoothness of the universe, the suppression of anisotropy, the very escape from BKL chaos, all depend on c being large, on the equation of state W being far greater than 1. Make that slope a little gentler, and the anisotropy wins. The contraction shatters into chaos. There is no clean bounce, and no orderly cosmos on the other side. Remember the dark energy epoch, tuned to last an immense and specific span before switching off at just the right time to trigger contraction. Remember the conversion mechanism, refined and adjusted until its non-Gaussianity matched the data. Remember the Galilean field, constructed precisely to violate the energy condition by precisely the right amount without collapsing into instability. This is not a model that runs on generic laws and routine chance. This is a model that works only when its parameters are set within narrow windows, windows the theorists must reach into and tune by hand. The fine-tuning that inflation was accused of has not been removed by the cyclic alternative. It has been relocated. Inflation must finely tune the flatness of its potential. Ekpyrosis must finely tune the steepness of its potential and the timing of its dark energy and the shape of its conversion. The precision did not vanish. It changed addresses. And precision is the fingerprint of decision. Consider a combination lock with many dials, each of which must be set to an exact value for the lock to open. Not approximately, but exactly. When you find such a lock standing open, you do not conclude that the dials spun themselves into alignment by chance. You conclude that something set them. The Ekpyrotic Universe is a lock with many dials. The steepness, c, the dark energy lifetime, the bounce parameters, the conversion timing. Every one of them must fall within a narrow range for a universe like ours to emerge from the bounce. The model does not explain why the dials are set correctly. It assumes they are, and then describes what follows. But the setting is the very thing that cries out for explanation. Here the proponent reaches for an escape, and it is the third claim, that ours is merely one universe among countless others, a multiverse, and that we observe finely tuned conditions only because we could not exist anywhere else. This is the anthropic answer, and it is most often associated with the eternal inflation picture rather than the ekpyrotic one. But it is the standard move whenever fine-tuning becomes embarrassing. So we must examine it. If infinitely many universes exist, each with different constants and different configurations, then somewhere the dials are set correctly by sheer statistics, and we find ourselves in that one because the others contain no observers to find anything. Examine this carefully, because it collapses under its own weight. First, there is no evidence for it. None. No other universe has been observed, measured, or detected, and, by construction, none ever can be. A theory that no possible observation could confirm or refute is not, by the standards of science, a scientific theory at all. It is a philosophical posture wearing the costume of physics. Second, the multiverse does not even solve the problem it was invented to solve. The mechanism that generates the infinite universes, whatever it is, must itself exist, must itself be lawful, must itself be structured to produce the variety it produces. You have not explained the fine-tuning. You have multiplied it. You needed one finely tuned universe. Now you need a finely tuned universe-generating machine plus an unobservable infinity of universes to run it on. And here is the most telling point of all: the inversion that the model's own authors hand us. The ekpyrotic theorists reject the multiverse. They are proud to reject it. Their entire boast of predictability, no quantum runaway that leads to the multiverse effect, is built on refusing the infinite, unfalsifiable fractal of inflationary bubble universes. They consider the multiverse a flaw, a loss of predictive power, a surrender. So the anti-design argument that leans on the multiverse cannot be borrowed to defend the cyclic model, because the cyclic model was built specifically to avoid it. The defenders of the eternal cycle and the defenders of the eternal multiverse cannot both be right, and each, in rejecting the other, exposes the weakness of the shared conclusion. One says fine-tuning is explained by infinite universes. The other says there are no infinite universes and the cosmos is precisely determined. They cannot both stand, but each, swung against the other, knocks the other down. There is a question underneath all of this that neither the cycle nor the multiverse can answer, and it is worth asking it plainly, the way a prosecutor asks the one question the witness has been avoiding. Why is there something rather than nothing? Not why this universe rather than another. Why anything at all? Ask it of the cyclic theorist and watch what happens. They will point to the previous cycle. Ask what grounded that one, and they will point to the cycle before it. Push the chain to infinity, and the answer never comes. It only recedes. Ask it of the multiverse advocate, and they will point to the universe-generating mechanism. Ask what grounds the mechanism, and the same recession begins. At no point does either picture produce a reason for existence itself. They produce only more existence, unexplained, stretching backward. The question is not answered. It is postponed forever, which is a way of refusing to answer it while appearing to. What does it mean that the deepest cosmologies we can build all fall silent at exactly the same question, the one a child can ask and no equation can touch? I want to be careful and fair here, because the people who built these models are not fools and not frauds. They are following the physics as far as the physics will go, and the physics goes remarkably far. The failure is not theirs. It is the failure of any purely physical account to step outside itself and explain why there is a physical world to account for. That is not a gap that a better instrument will close or a sharper equation will fill. It is a boundary, the place where the question stops being about mechanism and starts being about ground. There is one last refuge, and we must close it, because it is the most common of all. It is the promise that we do not understand the bounce yet, or the potential, or the dark energy field, but that science will eventually explain everything, and no intelligent cause will be needed. Listen to how the field actually speaks, and ask whether this promise is evidence or faith. The architects of inflation admit, in Mario Livio's words, that the theory has not been tested observationally in any detail. The architects of ekpyrosis admit, in Burt Ovrut's words, that theirs is a very radical idea. Paul Sutter, surveying the elegant cyclic construction, says plainly that it doesn't work. These are not the statements of a science on the verge of explaining existence. They are the honest admissions of brilliant people standing at the edge of what can be known and reporting that the ground gives way. Science will explain it eventually is not an argument. It is a promissory note written against a future that may never arrive. And it rests on a confusion about what science is for. Science describes how the universe operates, how branes collide, how fields evolve, how anisotropy decays under a steep potential. It is magnificent at this, and nothing here disparages it. But science cannot tell you why there is a universe to operate at all, why there are laws rather than no laws, why the dials are set for a cosmos that can hold conscious beings who ask the question. Those are not questions about mechanism. They are questions about origin and ground, and they have a different kind of answer. To insist that the mechanism will someday explain the origin is to mistake the map for the territory it is drawn upon. So where does the evidence lead when we follow it honestly and refuse to flinch? It leads to this. The universe, even in its most radical cosmologies, is not self-explaining. The cyclic model does not abolish the need for an eternal, uncaused reality. It confirms it, and then quietly assumes that reality is mindless. The fine-tuning of the model's own parameters does not vanish. It is relocated and concealed. The multiverse that might dissolve the fine-tuning is unobservable, self-defeating, and rejected by the very theorists in question. And the promise that science will close the gap is a statement of faith about the future, not a finding about the present. What survives the scrutiny is the conclusion the evidence pointed to all along. Behind the laws, there is something that does not depend on the laws. Behind the fine-tuned constants, there is something that chose them, because precision on this scale is the signature of decision, and decision is the act of a will. Behind the order that mindless matter cannot generate from itself, there is a mind. The eternal something that even the atheist cosmologist concedes must exist is not unconscious energy drifting through a hidden dimension. It is an intelligent cause, possessed of power beyond the universe it made, knowledge beyond the constants it set, and will beyond the moment it chose to act. The collision of branes, if it happened, was not the first cause. It was an effect, like everything else, of a cause that no equation contains. Let me bring this exploration to a close. We began with a number that refuses to appear, the tensor-to-scalar ratio, the missing fingerprint of primordial gravitational waves, falling year after year below 0.032. We followed that absence into one of the most daring ideas in modern cosmology, the Ekpyrotic Universe, born not from a single point, but from the collision of two branes across a hidden fifth dimension, and its cyclic descendants, in which the Big Bang is a bounce, and the cosmos may have no beginning at all. We watched the radion measure the gap between worlds. We watched a steep potential tame the chaos of a contracting universe. We watched dark energy turn from embarrassment into cosmic clock. We gave the model every fair hearing through the work of Khoury and Ovrut and Steinhardt and Turok and Ijjas, and we let its own builders speak. And then we tested its largest claims, and we found that they do not reach as far as they promise. The eternal cycle does not abolish the need for a first cause. It conceals it across an infinite past. The deterministic equations do not remove the fine-tuning. They relocate it into the steepness of a potential and the timing of a field. The multiverse that might explain the precision away is unobservable and self-defeating, and the cyclic theorists reject it themselves. And the promise that science will someday close the gap is faith dressed as patience. Strip away the machinery, and the universe still cannot account for its own existence. Something uncaused stands behind it, and the order, the information, the precision written into every constant point to that something, being not blind, but aware, not matter, but mind. An intelligent cause, with power, knowledge, and will. If you found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds. Two branes drift toward each other across a darkness we will never see. And in their meeting, the story says, all of this was lit. But even if it is true, even if the universe has bounced through cycles beyond counting, the oldest question waits on the far side of every bounce, patient and unanswered by any collision. Not how the fire was kindled, but who, before all fires, willed that there should be light at all. Good night.